Hello everyone, up next I want to talk about what we call or refer to as the power reducing or half angle formulas. And so all these formulas are going to be derived from our double angle formulas. We're just going to talk about our sine and cosine versions of these power reducing or half angle formulas, although there of course are versions for other trig functions as well. What we're going to see is that these power reducing and half angle formulas really are nothing more than our double angle formulas for our cosine function, just rewritten and expressed in some slightly different forms that makes them more suitable for the purposes of reducing a power or working with a half angle instead. And so we're going to go ahead and start by deriving these power reducing formulas, which come from the second and third versions of our double angle formula for our cosine functions. All right, so all we have to do to come up with our power reducing formulas for our sine and cosine function is essentially solve these two versions of our double angle formula for our cosine function, either for sine squared of theta or for cosine squared of theta. So let's go ahead and do that together. If we want to solve this first equation for sine squared of theta, we might add 2 sine squared of theta to each side. That'll give us 2 sine squared of theta plus cosine of 2 theta is equal to 1. We then subtract cosine of 2 theta away from each side of our equation. That lets us know that 2 times sine squared of theta is equal to 1 minus cosine of 2 theta. And then to finish it off, we divide both sides by 2. And we get our first power reducing formula, the one for our sine function. It tells us that sine squared of theta is equivalent to, or can be rewritten as, 1 minus cosine of 2 theta all over 2. So we can follow some very similar steps to find our power reducing formula for our cosine function. We're just going to take this other version of our double angle formula for that cosine function, but this time we're going to solve for cosine squared of theta. So if we just kind of flip our equation around, we get 2 cosine squared of theta minus 1 is on one side, and cosine of 2 theta is on the other side. If we want to solve for cosine squared, we got to get it by itself. So we might add 1 to each side as that first step, 1 plus cosine of 2 theta. And well, now we can solve this one a little bit quicker. Our last step, just like in the previous version, is to divide both sides by 2. And here we see that 1 plus cosine of 2 theta all over 2 is equivalent to cosine squared of theta. So these two power reducing formulas look very, very similar. The difference is whether we take the sum or difference in that numerator. All right, so we have our power reducing formulas for our sine and cosine function, but what are they used for? Well, they will occasionally be used to help us solve some trigonometric equations, but the real purpose, what we use them most often for, is in second quarter calculus or in integral calculus, helping us evaluate integrals of powers of trig functions. All right, there's one last little set of identities I want to derive in this video, and that is the half angle identities or half angle formulas. So just like how these power reducing formulas are really just alternative versions of our double angle identity for cosine, our half angle formulas are just going to be alternative versions of our power reducing formulas, although we could also say they're alternative versions of our double angle formula for cosine yet again. So there's really only 2 steps we take in order to go from our power reducing formulas for our sine and cosine function to our half angle formulas for our sine and cosine function. The first is a simple substitution. So remember, these power reducing formulas or identities work no matter what our input or angle is. So if we thought of this in terms of a, we could write it as sine squared of a is equal to 1 minus cosine of 2a all over 2. Now if we want to end up with theta over 2 in our formula instead of theta or a, we just make a substitution. We can set theta or a equal to theta over 2. So basically, if we replace a theta on this side with theta over 2, we just have to make sure we also replace every other theta or that theta on the other side with theta over 2. So if we make that substitution or replacement, the left-hand side becomes sine squared of theta over 2, and that's going to be equal to 1 minus cosine of, remember, we're also replacing this theta with theta over 2, but those factors of 2 would cancel out, giving us just cosine of a single theta. It's still really saying the exact same thing, just written from a different perspective, right? So if this is our angle theta, then on the other side we have twice that angle. Well, now if this is our angle theta over 2, on the other side we still have twice that angle. Twice that angle is now just theta. And so now to finish solving this, we just take the square root of each side. So we're just trying to get sine of theta over 2 by itself. So we have to take the square root of this fraction, 1 minus cosine of theta all over 2. And remember, whenever you are solving an equation by taking a square root, that is, you are the one introducing the square root, we have to introduce a plus or minus sign along with that to make sure we cover all the possible solutions. And so this is our half angle formula for our sine function. It says sine of theta over 2 is equal to plus or minus the square root of the quantity 1 minus cosine of theta, all of which is divided by 2. So an important question we might be thinking about is, how do we know which solution to take, or do we take both solutions, the positive and the negative? And the answer to that is we're only going to take one of those solutions. We have to determine whether the solution we want is positive or negative by doing a little bit of analysis or an investigation into that angle of theta over 2. So the way we usually go about doing that is we determine the quadrant in which this angle theta over 2 lands in. Remember, this angle theta over 2 is going into our sine function, and then we just look at that quadrant and see is sine or the y values on our unit circle positive or negative in that quadrant. That'll help us determine the positive or negative square root as our solution. And so, as you might guess, we have a very similar, almost identical process for deriving our half angle formula for our cosine function. We start by taking our power reducing formula for our cosine function and replace that angle of theta with theta over 2. So that gives us cosine squared of theta over 2 is equal to 1 plus cosine of just a single theta also over 2. And so again, to finish this off, we take the square root of each side. Square root of the left-hand side cancels out our exponent of 2, and that gives us plus or minus the square root of our right-hand side, or plus or minus the square root of the quantity 1 plus cosine of theta divided by 2. All right, everyone, in this example, we are told that tangent of theta is equal to 8 over 15. Our angle theta is between 180 degrees and 270 degrees, so it's in that third quadrant. And we want to use that information to help us find the exact value of cosine of theta over 2, or cosine of half of our angle. So you may have guessed that we need to use our half angle formula for our cosine function to help us do that. And so in order to use our half angle formula for our cosine function, there's a couple things we need, one of which is the value of cosine of our single angle theta, and then we also need to determine whether cosine of theta over 2 should be positive or negative. So let's go ahead and start by finding cosine of theta, and we're going to do that using the given information about tangent of theta and some right triangle trigonometry. All right, so we're setting up our right triangle here, and we know that tangent of theta is equal to 8 over 15. So in our right triangle interpretation, tangent of our angle theta gives us the ratio of the side opposite to our angle theta divided by the side adjacent to our angle theta. So we can think of the side opposite of our angle theta as having a side length of 8, and the adjacent side length would then be of length 15. The only thing that is missing in this right triangle now is the length of that hypotenuse, and we can find that using the Pythagorean theorem. We know 15 squared plus 8 squared is going to give us 225 plus 64, that's 289, and then when we take the square root of that, we find that the hypotenuse is going to be 17. So I just found that hypotenuse value using the Pythagorean theorem and the information about the other two given sides. And the idea is, now that we know that last side length is 17, we have our right triangle set up and we can use it to evaluate cosine of theta, because remember, cosine is the value we need in order to use our half angle formula. We'll have to be a little bit careful when evaluating cosine of theta, because when we set up our right triangle, we're not taking the quadrant in which our angle lies in into account. We know that our angle theta is between 180 and 270 degrees, so that's going to put it over here in the third quadrant, where sine and cosine are both negative, so we know cosine of theta is going to have to be a negative value here. So with that in mind, we can now find the value of our negative cosine. It's going to be the adjacent side length divided by the hypotenuse, or negative 15 over 17. And so we know cosine is going to be equal to negative 15 over 17. The last thing we have to determine is whether cosine of our half angle, cosine of theta over 2, should be positive or negative. And to make this determination, we always have to use that information about the original angle that was given. And from that information, we can usually derive some information about our new angle of interest, in particular theta over 2. So we know theta has to be between 180 and 270 degrees. So if we divide all three sides of our inequality by 2, it tells us something about our new angle of interest, theta over 2. It says theta over 2 is going to have to be between 90 degrees and 180 degrees, or in other words, in the second quadrant. And what do we know about our cosine function in the second quadrant? We know it is negative. So that's how we determine that our cosine of theta over 2 has to be the negative square root. And now we can evaluate that square root using our information about cosine of just theta. So we know cosine of theta over 2 by our half angle formula is negative 1 times the square root of 1 plus our cosine value. But here we're adding a negative 15 over 17 to that 1, and then we have to divide it all by 2. All right, so we have to, of course, simplify this expression underneath our square root. We can't leave our final answer in this unsimplified form. So the first thing I would do is combine those quantities in the numerator, 1 minus 15/17, and that'll simplify down to 2/17, right? I can think of that 1 as having a common denominator with a second fraction, which means I have to write that 1 as 17 over 17. We then take the difference by subtracting the numerators, and 17 minus 15 is where I get that new numerator of 2. So our numerator simplifies to 2 over 17, but we have to divide that by 2. And there's lots of ways to kind of think through that. You can either multiply by the reciprocal or just do the division. Either way, you should end up with 1 over 17 underneath our square root. And we can also think of this as negative 1 over the square root of 17. The last step we can do to simplify this is rationalize the denominator by multiplying both the numerator and the denominator by that square root that is showing up. And so if we do that, it ends up simplifying to negative square root of 17 over 17. That is our exact value for cosine of our half angle for cosine of theta over 2.